Hello, good morning, and welcome to Dallas, Texas. You join me and Alyssa visiting Texas Instruments. Well, we're all familiar with Texas Instruments because they pretty much do everything. They're involved with aerospace applications, automotive, and of course, calculators. But today we're discussing some of their automotive-related topics and specifically some of their technology that enables software-defined vehicles. SDVs are nothing new to this channel. We've been discussing with many OEs different software architectures and electrical architectures to enable an easier to manufacture and easier to update vehicle for OEs to give the customer a better ownership experience. Well, today we're going to be discussing some of the actual silicon that goes onto boards that helps make this type of application possible. I'm really excited to be visiting with Texas Instruments because they are on the bleeding edge of some really cool stuff that's coming into the automotive sphere over the next few years. And so today we essentially get a preview of what they're working on, and it's called Remote Control Edge. We're going to be meeting with some experts today, going through exactly how it's going to work and also some of the benefits that this technology will unlock. So join me as we nerd out about some silicon on chips. I'm looking forward to learning. Well, guys, we're going to be meeting with experts from TI in the next few clips, but I essentially wanted to give you a high-level overview of what we're going to be digging into in regards to Remote Control Edge. So this, for example, is a valve that goes inside of an electric vehicle, many of which you would be familiar with, that is controlled through software. So think about it when you precondition a car. This is just one of a million examples, but you're driving down the road, you precondition to a charging station, and you need to warm up the battery pack. Well, you've got to change the valving inside the thermal system so the battery can warm up. Well, a lot of times that is done through localized controlling of an actual valve like this right here. And that's not great. It means you need extra wires, you need a bunch of extra software that goes on individualized chips that can't be updated. We've heard so many times of existing automakers and even new automakers where it's like, hey, our software updates can update some modules on the vehicle, but not every module on the vehicle. And also, you know, there's a tier 1 supplier, tier 2, tier 3 supplier that you have to call every single time you want to make a software update to a vehicle, and it can take months. We've, of course, on this channel covered the trend and seen the trend of more centralized control over the entire vehicle and its subsystems, but also the ability to update them very quickly and very rapidly, where the automaker can own more of the software, where they don't have to call a tier 1, 2, and 3 supplier every time they want to make a change to a seat motor or, you know, some function in the headlight, for example. Well, situations like this and TI's Remote Control Edge will essentially take the software out of this valve and move it to a centralized source so that it can then just be controlled from a central ECU. And that is a trend in the auto industry that to the end user, the end customer, you may not notice every time you hit a button, but every time you get a software update or every time you can spend less money on your next car, you'll start to notice and feel, and it's going to change the game. It's still relatively new with only a handful of automakers going to zonal control type architectures, but TI is here, they're ready, and they have some really cool software to enable, software and silicon, to enable remote control of a ton of vehicle subsystems. So we're going to actually head inside and meet with this person named Donovan. And Donovan is an expert when it comes to TI's offerings and the entire industry as a whole with remote control operation of window regulators, door mirrors, seat heaters, all the above. He's awesome. So join me as we head inside to meet with Donovan to discuss this in detail. Well, guys, you join me inside the Texas Instruments super secure building. I have to add a lot of badges, a lot of different passes to go through. But you join me with Donovan. Donovan, welcome to the channel.
Nice to meet you.
Same here. And for those of you at home, Donovan is the general manager of power electronics and lighting at TI. And so when we talk about car nerd stuff, you and I, you're a whole nother level, but it's awesome. You're basically making cars work for the future.
Exactly. So we're a little bit deeper into the electronics of all the cars and what's behind enabling a lot of the features you see in modern vehicles today.
So I was just outside giving everyone an example of, sort of an OE that everyone would be familiar with, a valve, and
Sure.
how it's controlled. And I think I did a really poor job of explaining. And so my understanding is you would essentially have a command. Let's say you needed to change this valve, the old way of doing things.
Yes.
You would then have to send basically one set of control or command to this valve. It would then have to go through its own onboard software system to then power up and control the valve.
Exactly.
And the future with Remote Control Edge is what? How is it different?
So the idea with Remote Control Edge is essentially you no longer have any localized software at all. The idea is that, again, the same commands that you're sending to control the valve, you're actually now sending even lower level commands to actually control the motor itself, and maybe even monitor diagnostics to understand, do we reach the right position that we wanted to move that valve, or have we stalled or incurred some sort of fault? So the idea is, again, upstream somewhere else, you're now sending a localized lower level command to actually directly drive the valve itself, instead of having today where you have some sort of microcontroller with software that's translating that message and then running its own localized software real-time control to control the valve.
So yeah, today you would have to send like a CAN signal or even a LIN signal to a device, and there's no way to really ever update the way that device works once it's installed.
It's possible. It's just a huge pain and struggle for, again, OEMs, or again, working with the tier ones that maybe makes that valve to then go and update in that whole process. So really centralizing that software simplifies that piece.
So let's back up a little bit. So what is TI's Remote Control Edge offering essentially going to be? It's the ability to control not just a valve, but headlights, window regulators, heated seats, everything, any vehicle function from a centralized source.
Exactly.
Yeah, so maybe you can tell a little bit more.
So the idea, again, is I put up a bunch of different actuators basically to give some more visual context in terms of the different types of applications that this concept can be used on. But again, it's the same concept everywhere, centralizing software and moving that localized control to a central box, but still having the local actuators such as LED drivers for, again, headlights here, or motor drivers for pumps and valves, even things like wipers or the door here in the back, windows. And so again, the idea being that we are offering solutions in silicon that act as that bridge to receive communication or commands from some upstream module and ultimately translate that down to low-level hardware control. So again, this could be a signal just on-off, or again, a motor driver to turn on or off. It could be also speed control of the motor. It could be digital communication localized like SPI, I2C, and different local protocols there that will be used to, again, configure these drivers, like LED drivers or motor drivers.
Yeah, I mean, it's really more than just one offering. It's like a whole industry shift of how cars are controlled.
Yes.
One really cool example, I think we can mention that TI was integrally involved in a over-the-air software update for an American OE to gain matrix functionality in the US.
Yes.
So using your technology, you essentially went from auto high beams on and off. Because you also, we should mention, make the LED drivers in headlights, which are really cool. So lighting nerds out there, which I am one of, you guys make a lot of that, which is cool. But essentially having so much more, module level control, but also back to vehicle function. You could go from on-off headlights to matrix function with a software update.
Exactly. And again, the idea being that these remote control LED drivers, essentially, all you need to control them is, again, update that centralized software. So if you want to change how your lighting pattern works, or maybe update features like adaptive driver beam, all that, again, that updated software sits somewhere else. At the end, you just have hardware here with our silicon that, again, is just bridging that communication and then actually driving the LEDs.
It makes so much sense looking at it from now as to how this should all be done, because with basically cars being computers on wheels and much less just mechanical devices, having centralized compute is the most important thing, I think, for making sure that vehicle is relevant, but also not just for a one model specific. Let's say you're a large OE that makes 50 different models.
Exactly.
You don't have to then make 50 different versions of everything. You can make one centralized computer that can be adapted to a bunch. So maybe we can actually use this door as an example.
Exactly. And I think the other cool thing that OEMs get the advantage on is ultimately wiring is the other piece. But even when you think, again, a door, you can have different functions in the door. Typically you'll have side mirror adjust X, Y just to move the mirror for the driver. You'll also have the mirror folds. You may have turn signals here. And then, of course, you have your window. You may have additional sensors for the door handle for your car access. All these different features that could sit in the door alone. And the idea being, again, is you have different models of cars or even different trims of cars, you can then simply add more features through hardware and then simply update that software somewhere else. And then when you think about an OEM, again, like you mentioned, that has, platforms and different vehicle models, all different sizes and a huge range of cars, the idea is that that same software can be updated and maintained simply and then updated for specific cars. So they can develop it once or maybe maintain it across just a few platforms, simply update that central box or the zone control module wherever that sits, and then you still have the hardware here locally to control and add those features and functions.
And let's talk about wiring really quick as well, because the benefits of doing that type of situation from a wiring standpoint are insane. You essentially only need to run 1 or 2 communication lines to the entire door, a power, and is that it?
And likely ground. So basically 4 wires.
Yeah.
And so that's the real advantage that we see, right? So again, you've seen the centralization of vehicle architectures to fewer and fewer electronic control modules in zones, typically today. But the challenge again is if you were to think about that zone maybe sits along the firewall by the driver here, you still have to run all those wires through the door hinge.
Totally.
Every single motor you have, every single LED
is
at least a wire, if not 2, maybe even more.
I mean, if anyone ever peels back the little connection point in their car, you'll see a wiring harness that's about that thick running to a door. And if you can go from 80 or 100 wires down to 4.
Exactly.
It's
significant savings.
Yeah.
And then the idea again is if they wanted, depending on how you want it, you could still have a centralized control module, kind of like what we're showing here.
Yeah.
Or you could again still have a remote control motor in each of the functions you have. So however they decide they want to control that functionality can be again modular, and then you can change in features and functions by simply adding the electrical hardware and updating your software upstream to then control those different functions.
So let's pretend I'm an OE really quick, and I want to get into exactly how this situation works. Actually, maybe we can use this TV over here to explain a lot of what we're discussing in sort of a wiring diagram. So you have your central compute. This is where the command source is from.
Exactly.
Let's say you hit the window down switch, or you put your seat heater on. That goes there first. Then what happens?
So basically the idea is the central compute will then send a command over typically a high-speed network that's already in the vehicle today, Ethernet likely, 100 megabit or gigabit, send that command over to a zone. The idea now is that the zone actually could have the actual real-time control of that function. So let's say you want to adjust your seat. So basically that command could go to the central compute. He then tells the zone, all right, you need to adjust the seat, this position. The zone will then actually run the real-time control to monitor the seat motor. One, send the signals remotely to control the motor, and then also monitor, for example, the position. So if you had like memory seats, right, and you come in, you basically would automatically adjust to your position. So it knows that position. It actually stores that information in the zone, sends the signals again to control the motor, monitors the real-time position of that seat, and then basically make sure that you get to the right position there.
And what would happen previously? Let's say we wanted to, hit a memory function in the old school days.
Yes.
What would that be like?
So usually it would be much more local controlled, right? And the idea being, again, you have a local microcontroller there that stores all that memory, maybe in the seat or in the door panel, wherever they control the buttons. And the idea being that, again, that microcontroller has to be programmed with those different memory options and is probably limited based off of whatever, again, hardware and software it's initially set up with. And the idea would be that maybe the central compute wanted to adjust the seat. It would send a message to that module that, again, has software in it that would then have to then decode that message and actually perform the function. So the real-time performance would still happen at the edge of that, or that edge ECU there controlling the seat, instead of being done in the zone. And the other piece, again, going back to the software piece, is that the software sits in that seat now. It's no longer in the zone, it's not centralized. So if you ever want to change it, or maybe, hey, we need 4 settings. Maybe I have teenage kids that I want to be able to drive and have their own settings. I can just automatically update it, versus in a car with the set hardware, set software, you're stuck with whatever was designed for.
Yeah, and it's really this Y split of old school and new school is how we view them when we review cars is, okay, is this a software updatable vehicle to almost every module? And the answer is that's really hard unless you're doing zone controllers with remote control.
Yes.
Because if you had to update every single little computer chip on a car, it would be impossible.
Exactly. It's possible, but it takes time, right? And that's always a thing. And then is it even worth it by the time you get it done? There's another update that you want to run. So that's the whole challenge of it. And again, to your point, what we're doing now is we're able to now centralize that software, but at the same time still be able to provide localized control, and then also simplify that over their update time. So now you can technically adjust all these different features much easier, right?
Yeah. So explain it to me like I'm in OE, for example. I am a large, final assembler of vehicles. I have, 50 different models. What is the actual process to implement this into my vehicles?
So the idea, let me actually change, I'll have a better diagram.
Oh,
here.
cool, nice.
So basically the idea is, again, historically you had a microcontroller, maybe you worked with the tier 1 supplier that would actually develop the software, actually do all the hardware abstraction for controlling these load actuators, again, LED drivers, motor drivers, whatever.
And that's when the OE has nothing to do with it,
exactly.
right? They're just
you say,
saying,
hey, I want this functionality, they go and design it, they do it, right? I want 2 memory seat positions, and I want this many motors and these features, they go and design that system.
And the OE almost has, at that point, no idea how it even works.
Exactly.
They're just putting it in the car.
And all they do is send a command, hey, do this, hey, do this, and they don't have to deal with it, right?
Right.
The idea here is it's similar, but the key piece is that now you just have a bridge. So this is again where we're offering from TI is these solutions to bridge this communication in the vehicle network to actually load control. Again, LEDs, motor drive, all different applications. But the software again moves somewhere centralized. Again, it could be that central compute, it could be a zone. But the idea is, again, now you have all your control for vehicle functions in that zone. This purely becomes hardware, and you're just receiving these commands low level to then control these load drivers. So all they need to do is understand what commands they need to configure these load drivers and ultimately make sure that they can get the data and run their control algorithm real-time upstream.
Yeah, and I guess a lot of times I would say even old school traditional automakers would say, well, when we deliver a vehicle on day one, we just want it to stay the way it is. We've done all the development work and we're done.
Right.
And clearly that is not the way of the future anymore. For example, on one of my cars that I used to have, I got a software update that adjusted the windshield wiper position like 3 degrees. And the reason was there was a parked position for visual effect. And then when it was above, I guess, 30 miles an hour or whatever, it would move so it's a little bit slipperier with the air. And you could never do that unless you had a remote control situation, because if you had just bought a windshield wiper from a supplier, you have on, off, and speed. But the windshield wiper position needed a software update. And you would never imagine that would happen until after series production started.
Exactly, and that's the thing, that's the really neat part of this whole software-defined vehicle concept is what you can do with it. I mean, there's endless possibilities. I think making sure that hardware is updatable, at least the software to control the hardware is updatable, is important. And this, again, OEMs will find different use cases, like something that, again, you may not think of till later on. It's like, hey, maybe we can optimize the windshield wiper for better aerodynamics. It could be even things like your battery pack for a full battery electric vehicle. How do we optimize, maybe power consumption in the vehicle? And maybe I need to update when the heated seat, how it's operating to be more power efficient. So there's all these little bitty ways that software-defined vehicle can be implemented. This is just a way to really enable that and make it easier.
So what is TI offering to tier 1 and to OEs? Because I think OEs are trying to shrink that supply chain down, and they're trying to develop relationships with companies that are farther down the supply chain.
Exactly.
So when an OE approaches you, just for my own curiosity and our viewers, are you saying, hey, here's the actual silicon chip we're going to put in? Do you say, hey, here's the software communication so that you can write your code to then work with our bridge? How does that work?
So basically, maybe I'll walk through the hardware and then the software piece.
Yeah,
right? So from a hardware perspective, again, we'll have the bridge device. So this will be like again, 10-base T1S, CAN FD Lite protocol. Today we even have UART over CAN capabilities. The idea again is that this device can receive some sort of standard protocol and basically translate to local control. So these are all local communication for different hardware in the system. So we offer this as the main key bridge, and then we also will have the actuator sensors, additional logic that may be needed, other circuit components. Again, this could be like LED drivers, half bridge, full bridge drivers for motors, things like that. The key thing from the software side is a very good question, right? So I think ultimately OEMs will want some level of, in that upstream control module that controls all this hardware, they are looking for ways to abstract and make it easy for them to implement their control signals, right?
Absolutely.
So just like today, they want to send a command, hey, move the seat,
Yeah.
roll the window up, keep it fairly simple. So they're looking for us to, how do we provide software APIs, basically application program interfaces, to make it easy to just simply say, I want to roll the seat up. Well, I need to translate that to essentially send this message, which then controls the motor driver and configures it in this specific way.
Right.
So that's where we're looking at developing these types of APIs to make it easier for OEMs to implement that in their software stacks, and so they can get up and running a lot faster with these different systems.
And there also needs to be two-way communication as well. Like you need the response to say, hey, this required way too much force to move, like windshield wipers stuck in snow, or, you used a great example earlier when we were talking off camera about, you know, how window motors have to go up, and with a pinch sensor, they have to come back down. But you had an interesting concept around that
again,
as well.
that's where it's still very early, right? This whole remote control concept. It started in lighting primarily because lighting is very simple. Less of this real-time control has to happen in the light, for example. You're just basically matrixing lights, things like that. But when you bring up like something like a window, when you're rolling up the window, you need to detect a pinch or a force and basically roll down, because you can't crush someone's hand, or, you know, we've had issues with other OEMs where maybe they need to have software updates to fix these types of problems.
Yeah.
And so the key thing again is OEMs have to decide, working with tier ones that have some of this knowledge on how do you actually implement that real-time control loop, and can you do it purely with remote control, where you're sending just all raw dumb data all out to the central compute to process, or do you need some sort of reflex that is implemented in this transceiver or in this bridge, right? So the idea being, maybe just like in our human body, right, we have a natural reflex to respond. If I do automatically see this sort of torque, I need to automatically just roll down without the command of a central compute or a zone.
Right, because if that's happening at the same time you're starting up the vehicle and you're adjusting a million other things, I mean, there are situations where you can overload the communication system.
Exactly.
So just having that quick reflex is a really cool function that can be built in.
So those are all the little nuances that we're still trying to work out the details of by application, right? Every application is a little bit different, and, you know, Windows one, but there's other cases. Seats are another similar case.
Sure.
But the idea being, again, what do we need to integrate potentially in this transceiver, in the silicon, to help implement those types of reflexes. So again, it makes it easier and it doesn't overload the communication network.
Right. This is super fascinating. Absolutely love it.
It's pretty exciting. It's a very different way of implementing it. A lot of new challenges will come with the implementation.
Yeah, and what's needed is, you know, for you know, a lot of folks imagine that some of these new entrants, Chinese automakers, even some of the newer US automakers, like they own everything in the car. But the answer is just not the case. They still have to, they're not making their own silicon to go in. That's where they still rely on, you know, tier one, tier two, tier three. You guys are heavily involved with almost every automaker. It's insane. And so, you know, having this type of experience from working with everyone to then allow new and old automakers adopt can change the industry really quick.
Exactly. And that's a big goal here is, again, how do you standardize this, right? Because the key thing is we don't want to make anything proprietary that you're stuck with one supplier. Because again, from an OEM perspective or a tier one perspective, generally you'll want some sort of multi-source. So again, you can guarantee you can get products from different suppliers, different regions. The idea here, again, is these are based off standards, right? And again, a lot of these standards are still in progress, but this will all be standardized. So the idea being, from the OEM perspective or tier one, I just need to send this specific communication message. How that gets handled is standardized, and what that message looks like is all standardized. So there's no proprietary. You're not stuck with any single supplier as well.
You also need
this will help accelerate that.
Exactly. Yeah, you need the whole industry to catch up to this. So you need to kind of support some legacy protocols at the same time.
Yes.
And what's your impression on different voltage levels in the vehicle? Because I know this is not necessarily what we're discussing now, but you know, we're starting to see this trend towards 48 volt for communications. This type of system can handle that?
Yes. So typically the communication network voltage will be agnostic of the actual supply voltage. Usually they step it down. CAN's 5 volts, Ethernet's even lower, 3.3 typically.
Oh, cool. Yeah.
LIN's battery. So when you look at communication, they will be able to support 48. Biggest one is LIN, which is more legacy anyway. So how that can support 48, you'll still likely need to step that down to 12.
Yeah.
Generally, the main concern with network and communication is just fault modes. So can you handle a short to a battery 48 volt signal, or any other signal that could be 48 volts? So that's really more fault scenarios that you need to be able to survive. But in general, the actual voltage that they operate will already be a much lower logic level voltage.
Makes sense. Well, really cool. Thank you for this presentation.
Yeah, of course.
We're actually going to go see it work.
Yes.
So we're going to run up to a lab. We can't show inside the building because it's like this labyrinth of how this building's insane.
It's huge.
It's crazy.
It's very big.
I mean, just driving by it on the road, we're like, oh, we're going by Texas Instruments. Still going by.
It's a huge, and this is just the one South Campus building. We still got the North. So
it's insane. So we're going to run up, meet with Madison and yourself, and then we'll essentially go through sending a command and watching the communication go through, which will be really fun for everyone.
To actually show that bridge, to give a little bit more visual context there.
Should be great. Well, thanks for this presentation. It was great.
Yeah.
Well, guys, you join us after a 25-minute walk. It wasn't that bad. Up here to one of the lab spaces. So, Donovan, we're going to go through with your colleague Madison a lot of what we're showing and this actually in progress and working, what we discussed. But I wanted to briefly just reiterate some of the different communication topics and communication signals that you guys can support with Remote Control Edge.
Yeah, so in general, remote control eggs, we're working on solutions for 10BASE-T1S Ethernet, which is another protocol that's starting to emerge. Canopy Light that you'll see here today. And then, of course, outside of just remote control edge concepts, we still support other protocols like your standard 100 gigabit Ethernet. Also, standard CAN FD, CAN SIG. LIN is just still existing in the vehicle today, so we do also have those available as well. But for remote control, again, 10BASE-T1S is and Canopy Light are our two protocols we're primarily focused on.
Yeah, and that's really the next generation of cars going that way anyway. So in this display, Madison will actually walk us through it, but maybe you can just at a high level tell us what we're actually seeing here, because we have a fan that's being controlled,
Yes.
but maybe you can explain how that's happening.
So again, we want to think of this as what it would look like in an actual car. So the idea being that maybe this is a seat fan, for example, that we're going to emulate control of remotely. The idea is we're probing and we're sending actual messages from one board via a CAN bus, and then we're receiving those from the Canopy Light responder, and then controlling again the fan itself, all just through that remote control messages. And I'll let Madison walk through more of those.
Yeah, very cool. Well, thanks for joining for the video, Donovan. It was great to see you. And Madison, I'll bring you in if that's okay. Yeah. Welcome to the channel.
Hi, Madison. Nice to meet you.
Yeah, same here. So, Madison, what's your actual responsibility at TI?
So I am a systems manager, responsible for zone and body domain controllers. So I'm within, the body electronics and lighting team, and with all of these architecture shifts that are happening around zone architecture and SDV, my team is really helping look at those systems and see what's coming next and how we can help today.
Awesome. Very cool. And you have developed this nice display of it actually working, because we're talking a lot of theoretical concepts. It's still early days for this type of technology, but you've made this sort of prototype-y display, which I love. So maybe you can walk us through all of the componentry that we're seeing here, and then actually we'll watch it cycle through and work.
Yes, for sure. So, we have a lot of wires going on here. So this is we just got this together. So this is actually a new part that's releasing this week, actually.
Oh, cool. Congrats.
So we're really excited about it. And I know Donovan has kind of talked a little bit about it, but in general, what we have is this is going to be representative. So this is one of our microcontrollers. It's one of the MSP 430s you can see here in the block diagram. So this is acting as our commander. So it's what's emulating what a zone control module would be in the architecture.
Mm-hmm.
So it is then sending the communication to our CAN FD Light bridge device, our responder.
Yep.
So in this case, this is TCAN 5102. So we have a transceiver that's taking it in and then sending it out over TX and RX to the responder, which is then acting as a bridge to actually translate that into SDI, SDO, SCLOC SPI, I2C, whatever communication is needed.
Sure.
In this case, we have our smart eFuse device.
Mm-hmm.
So this is what's actually providing power to the fan. So when the CAN message is sent from the commander, the responder then takes that and sends it out over SPI, telling the high side switch to turn on or off.
Right.
And that's where you can see the fan actually turning on or off in this case.
And the bridge controller is really cool, because this is what's taking a lot of the, I would say, new school signals from the vehicle, from like the infotainment side or customer request, and basically translating it, communicating it, sending it down the line so that you can control those specific applications, such as a fan or a seat heater or a seat motor or window controller, whatever it might be.
Exactly. So all of the commands are starting here, and this is just actuating all of that further along.
Super
but yes,
cool.
This is really the key device for our CAN FD Light that we really want to highlight. It's really cool new technology that we're going to hopefully see soon in vehicles.
Yeah, so is there anything specifically on the chip that you wanted to highlight or mention? I know this is brand new, but if you can zoom in, come on in here, you can see a really nice looking thing. Now, obviously, you guys aren't printing the PCBs. You're doing more of the silicon in there.
Mm-hmm.
But maybe you can highlight anything specific on the chip that would be interesting.
Yeah, so I think really the main thing is that it's the bridge device, right? So it's what's taking in, so you have this PHY that's actually taking in the CAN high and CAN low and sending that data such as something this guy can interpret. And this guy can do a lot of different things. It can do SPI, it can do I2C, it can do general GPIO control. It can do a lot of different protocols needed to control different things at the edge. In this case, we're just highlighting that it can do SPI for this particular device.
Yeah, super cool. Well, imagine this scaled up to a total vehicle would be wild. This is just obviously one millionth of what a car can do.
Yes.
But essentially, this can support a ton of different outputs.
Exactly. Yeah, it could be a lot of different end equipments in the end. So in this case, we're showing a fan, but maybe it's a door, maybe it's a seat. It could be a lot of different things in the vehicle.
Yeah. Well, thank you, Madison. Appreciate it. The display is super cool. Love to see this stuff early on in the development cycle. So thank you for showing us. And of course, one day we'll be able to experience this in a car, which will be really cool. Well, there you have it, guys. A day at Texas Instruments learning all about controllers, communications, and of course the remote edge, which is a really cool situation. Seeing that bridge controller work to take basically a vehicle command signal and then operating a fan at high level, yeah, seems pretty basic. But when you think about what's actually happening through that process, well, that's pretty cool. And if you scale that up to 1,000 different devices that need to be controlled by a centralized ECU, well, now we're talking about the future of cars. Absolutely love it. If you want to learn more about Texas Instruments automotive products, I'm going to leave some links down in the description. So feel free to peruse through and do some extra learning. If you want data sheets or even contact information, it will all be left down there. But a huge thanks to Texas Instruments for bringing us out here to Texas to learn all about remote control edge. We'll see you on another one again soon. Bye-bye.